I want to look at the relative nucleophilic strength of the halide ions, fluoride versus chloride versus bromide versus iodide. In order to do this, we need to look at several different features of a nucleophilic reaction. I'm going to focus on an SN2 reaction, but the same principles apply to a lot of different reactions. One of the things we need to consider is the relative size of these ions. When we depict them as letters, the F and the Cl and the Br and the I, they look like they're about the same size, but that's very far from the truth. I want to look more closely at the size of these ions. And I'm overemphasizing the size differences a little bit to illustrate my point. But what we see is the fluoride ion is much smaller than the iodide ion. And that has several ramifications. The first ramification is the fact that they all have the same charge. They all have a -1 charge. In the fluoride ion, that minus charge is spread over a very small area. For the iodide ion, that charge is spread over a much larger area. The charge is much more diffuse. The next thing that this size plays a role in is in the actual mechanism of the reaction. If we look at the mechanism of an SN2 reaction involving the fluoride ion attacks my carbon center from the back side away from the leaving group. I have 3 other things attached to that carbon. I get this transition state that has 5 things bonded around the carbon. The fluoride is coming in from one side, the leaving group is leaving from the other side, and when I go to my product, my fluoride is attached to the carbon center, and I've had an inversion of configuration. In the case of iodide, you can see the nucleophile is much bigger. If we go to this transition state, the iodide, the much bigger iodide, is in this transition state where there are 5 things bonded to carbon. This is very crowded. It's much more crowded, in fact, than the same transition state involving the fluoride ion. If we compare it to the transition state involving fluoride, again, there are 5 things around this carbon, which is not good because carbon only wants 4 things normally. So the transition state is crowded, but it's less crowded for fluoride because the fluoride ion is smaller. That means that the transition state energy for the reaction involving fluoride is going to be lower than the transition state for the reaction involving iodide. Therefore, fluoride is going to react faster, iodide is going to react slower, if all other things were equal. In order to kind of finish the picture, we need to look at the solvent, because the solvent plays an important role here. There are 2 types of solvents that you can have in an SN2 reaction. We can have polar aprotic solvents and polar protic solvents. In polar aprotic solvents, the solvents are specifically designed so that they don't interact with my nucleophile. Therefore, the reaction in polar aprotic solvents looks very much like this. We have a completely free nucleophile interacting with my carbon center that has a leaving group, giving me a transition state that looks like this. In this case, the deciding factor is which of these 2 transition states is lower in energy. And in this case, in the case of the polar aprotic solvents, the transition state involving the fluoride ion is lower in energy than the transition state involving the iodide ion, so the reaction with fluoride goes faster. So in the polar aprotic solvent, the order of nucleophilic strength is fluoride is greater than chloride, is greater than bromide, is greater than iodide. When we look at the same reaction in a polar protic solvent, we need to consider a few extra factors. We need to consider the fact that the polar protic solvents can interact with my nucleophiles. Polar protic solvents can hydrogen bond to my anions, my nucleophiles. I've chosen water as my polar protic solvent because it's small and I can draw easily and not hide up the features of this reaction that I'm trying to emphasize. In the case of fluoride, it's a small nucleophile, so it has a lot of charge concentrated in a very small area. It forms very strong hydrogen bonds with my solvent molecule. On the other case, iodide has a negative charge spread over a much larger area. The hydrogens on the water, or whatever solvent I have, do not hydrogen bond quite as tightly as they do in the case of iodide. I mean fluoride. Iodide hydrogen bonds less strongly. That means that it's easier for the iodide to lose its solvent shell and to act as a nucleophile. For fluoride, it's much harder for it to lose that solvent shell. It's much more tightly bound by my solvent, so it's not that good a nucleophile. So in the case of a polar protic solvent, fluorine is less nucleophilic, fluoride is less nucleophilic than chloride, is less nucleophilic than bromide, which is less nucleophilic than iodide. So the orders are reversed in a polar protic solvent.